Have you ever stared at a really complex differential equation and just felt completely stuck? Well, today we're going to learn this incredibly powerful technique to take that one big, messy problem and slice it into a system of smaller, much more manageable ones. So, let's dive in. So, just take a look at this thing. It's a third-order linear differential equation. At first glance, it looks pretty intimidating, right? I mean, where do you even start? But more than that, how would you tell a computer how to solve it? That's the real question, and that's exactly what we're going to figure out today. You see, the secret isn't really to attack this equation head on. It's to transform it. And this isn't just some clever math trick. This is the key that unlocks a whole new world of tools, from computers and linear algebra to solve these exact kinds of problems. So why even bother with this whole conversion thing? Well, there are two really big reasons. First, most of the really powerful computer algorithms that approximate solutions, you might have heard of things like the Runge-Kutta methods, they're all designed to work with systems of first-order equations. So this gets our problem into a language the computer can understand. And second, it lets us unleash the full power of linear algebra. We can squish the whole system into a single matrix and then use amazing tools like eigenvalues and eigenvectors to find the exact solution. It's basically the bridge between calculus and linear algebra. Okay, so how do we actually do this? The great news is there's a simple, repeatable recipe that works every single time. Let's walk through it together. The whole recipe is just about defining new variables in a really clever way. So we start with our original function, y, and we're just going to call it x1. Simple. Then we take its derivative, y prime, and we call that x2. And we just keep this chain going, defining x3 as y double prime, and so on, all the way up until we're just one derivative shy of the highest one in our original equation. And this right here is where the magic happens. Just think about it for a second. What's the derivative of x1? Well, x1 is y, so its derivative is y prime, which is exactly what we defined as x2. And what's the derivative of x2? That's y double prime, which is our x3. See, we've created this beautiful, simple chain where the derivative of each variable is just the very next one in line. Okay, theory is great and all, but let's get our hands dirty and see how this actually works in practice. We'll walk through a couple of examples. Start with a nice easy one, and then we'll work our way back up to that tricky third-order equation we saw at the beginning. All right, here we go. A standard second-order homogeneous equation. The highest derivative is 2. So how many new variables do you think we're going to need? Yep, exactly. 2. Our goal is to turn this one equation into a system of two first-order equations. So, following our recipe, the first thing we do is define our variables. It's a second-order equation, so we just need 2. We'll let x1 equal our original function, y, and x2 equal its derivative, y prime. Easy enough. Now let's build the system. The first equation is a gimme, right? It comes straight from our chain of definitions. The derivative of x1 is just x2. For the second equation, we need the derivative of x2. Now remember, x2 is y prime, so its derivative is y double prime. We find that by just rearranging our original equation to solve for y double prime. Then all we have to do is sum our new variables, x1 and x2, back in. Done. And here's the payoff, the final step, writing this system in matrix form. Let's look at that first row. It represents our first equation, x1 prime equals x2. So we've got a 0 in the x1 column and a 1 in the x2 column. Now the second row, that's our second equation, x2 prime equals negative 2x1 minus 3x2. So we put a minus 2 in the x1 column and a minus 3 in the x2 column. And just like that, we've turned our second-order equation into a tidy little matrix system. Okay, you ready? Let's go back to that monster from the very beginning. It's third order, so this time we're going to need 3 variables. x1, x2, and x3, which will represent y, y prime, and y double prime. Building the system here follows the exact same logic. The first 2 equations are easy. They come right from our chain. Derivative of x1 is x2, and derivative of x2 is x3. For that last equation, we need the derivative of x3, which is y triple prime. And if we look at our original equation, y triple prime is just equal to y. And since y is our x1, that means x3 prime is just x1. And when we write this system and a matrix, we get this really cool structure called a companion matrix. Notice the pattern? You've got this line of ones just above the main diagonal, and that's our chain of derivatives. Then the very last row is just made up of the coefficients from our original equation. It's this clean, predictable structure, and it's a direct result of our conversion method.
So a question you might have is, does this recipe only work for homogeneous equations, the ones that equal zero? Nope, absolutely not. Let's take a look at this one, where the right-hand side is a function of t.
The process is almost identical. We define x1 and x2, and our first equation, x1 prime equals x2, is exactly the same. The only difference happens when we solve for x2 prime or y double prime. We still get negative y, which becomes negative x1, but now we also have that plus t term that just tags along for the ride. That non-homogeneous part just becomes part of our system. Let's just take a second and appreciate what we've actually done here. You've just learned a technique that is absolutely fundamental for solving differential equations, whether you're doing it on paper or telling a computer what to do. I mean, look at this. This is the whole idea in a nutshell. We've taken one really complex problem, a single high-order equation, and we've systematically transformed it into a bunch of simple first-order equations. Now we're ready to bring in the heavy hitters, linear algebra and numerical analysis. And really, that's the key takeaway. This conversion, it isn't the final answer. It's the crucial first step. You've just successfully translated a complex problem into the language of linear algebra. So, now that you've built the system, are you ready to see what kind of damage we can do with eigenvalues?